Good day, everybody. Thanks for being here today. Our group is excited to present our project titled Anomaly Detection in IoT Network Traffic using Python and Power BI. As you may know, in today's digital world, IoT devices are widely used in homes, cities, and industries. But while they bring convenience, they also open the door to security threats. Our goal in this project is to detect unusual or malicious behavior in IoT network traffic using real-world data and data science tools. Our presentation comes with three key factors. The first is data analysis with Python, how we clean and structure our dataset. The second being security behavior analysis, which identify differences between normal and attack traffic. The last is advanced analysis, is where we apply machine learning and time series techniques to detect anomalies. To begin with, we'll walk you through how we prepare the datasets for analysis. This is a crucial foundation for any data science project, not only ours. So with the dataset, we use the ACI IoT 2023 dataset, which contains detailed packet level network traffic label. The network traffic label as either BEN, IGN, or different types of attack. Using Python libraries and like pandas, NumPy, and Seaborn, we cleaned the data, handled missing values, and extracted key features such as protocol type, port numbers, timestamps, and packet statistics. On this slide, you can see an overview of the steps we followed. We worked with a CSV file that included source and destination IPs, ports, labels, and other fields. After cleaning, we saved the results in a new file called cleandata.csv, which became the input for our next phases. With our cleaning strategy in more detail, we replaced invalid entries and dropped rows with missing critical values, handle missing data by filling numeric values and with medians, and categorical values with unknown. We also converted timestamps and created new columns such as hour and day in order to compute traffic level features like flow duration and average packet length. This visual shows the four-step data preparation process. The first being load and inspect. The second is clean the raw data. The third is impute and encode missing values. And the last is perform feature extraction. With this, we had clean, structured data set ready for behavioral and anomaly analysis. Now I will handle it over to Get to talk about our traffic behavior analysis.
In this part of the project, we focused on analyzing labeled traffic data to understand how malicious behavior differs from normal network activity. This behavioral analysis helped us uncover patterns that are common in network attacks, which we later used to train and validate our anomaly detection system. We broke the analysis into 5 key areas: the protocol usage to identify which network protocols are commonly exploited in attacks, the traffic labeling, where we classified each record as either benign or attack, the port behavior, examining which port combinations were frequently used during intrusions, the hourly trends to find what times of days attacks were most active, and device level behavior, analyzing packet count and flow duration to spot suspicious device activity. Here's how we structured our analysis step by step. We began by loading the raw dataset, followed by labeling the traffic accurately. Next, we generated overall summary statistic, then moved into protocol-specific analysis, and finally dove deeper into port behavior and device-level metrics by grouping the data across categories like source IP and timestamp. This structured approach helped us extract meaningful patterns from complex traffic logs. To make the data consistent, we standardized traffic labels by converting them into uppercase and trimming any extra characters. We then calculated the total numbers of benign and attack records. From there, we derived the attack ratio, which gave us a clear picture of how much of the traffic was actually malicious versus normal. This foundation step was key to making accurate behavioral comparisons. Well, from our analysis, we found some clear distinctions. Benign traffic showed stable, predicted protocol usage, smaller packet size on average, and fewer large volume flows. In contrast, attack traffic had spikes in the packet volume, unusual port combinations, and often employed aggressive protocols such as UDP floods. These behavioral differences provided strong signals for identifying anomalies and played a critical role in training our machine learning models. These behavioral insights form the foundation for the next phase, which focuses on automated detection using machine learning and time series analysis. I'll now pass it over to. In this final phase, we applied machine learning and time series analysis technique to detect anomalies in network traffic. Our workflow followed a structured 4-step process. First, we performed data preparation to clean and structure the network traffic logs. Secondly, we conducted a feature selection, choosing key indicators such as length mean, flow duration, source and destination ports, and the network protocol. Third, we implemented an anomaly detection model using isolation forest, which is especially effective for identifying rare and unusual patterns in large data sets. And fourth, we integrated time series monitoring to detect real-time traffic spikes and trends over time. Next up, we get to the implementation details. After pre-processing, we normalized the features using standard scaler to ensure they were on the same scale. We then trained our isolation forest model, which assigned each traffic flow a label. For example, 1 for normal behavior and -1 for anomalies. Once classified, we saved the result to a CSV file. This enabled further visualization and evaluation of the anomaly patterns detected by the model. Next up, we visualize the strategy. We get to the visualization strategy. To make the results interpretable, we used 2 main visualization techniques. The first one is that we use bar charts to display the distribution of anomalies compared to the normal traffic, helping us to see how frequent and severe these anomalies were. Secondly, we used line graph to highlight traffic spikes over time, giving us a visual timeline of unusual network behavior. These visuals allowed us to track, validate, and better communicate the performance of our detection system. Finally, we get to the time series detection. For continuous monitoring, we implemented a rolling window approach. Over a 10-minute sliding window, we computed the rolling mean and rolling standard deviation of traffic flow. A spike was flagged as an anomaly when the traffic exceeded rolling mean plus 2 times standard deviation. These thresholds helped us detect sudden changes in traffic volumes, and we visualized them on a timeline plot for effective anomaly tracking.
To conclude, we took a real-world IoT traffic dataset, cleaned and structured it, studied attack behavior, and applied machine learning and time series methods to detect anomalies. We also visualize everything in Power BI dashboard, making practical for real-time monitoring. Thank you for attention, and we welcome any question or feedback you have.